Okay, we are starting. The first question was on review worksheet 14, number 11, Maclaurin series. So our function is f of x equals natural log of 1 plus x. On a problem like this, if you're looking at the answer key, or if you've looked at the answer key, because I did make that available, right? Answer key should be up now. Answer key was not up yesterday when I handed the paper to Ross, but it is up now. And if it's not, I'm really confused because I made sure to make sure.
I think it's up because I've been looking at it.
Okay.
Oh, I found it. Leave me alone.
Okay, so she was in the wrong place, whatever she was doing. Got it. Okay. With a Maclaurin series like this, it's easiest for me to organize my information ahead of time and make the chart, and then write in the equation. So kind of like the chart I made with sine x and cosine x, right? So when I set that up, I set up 3 columns. The first column is the n column, and with the n column, I always start with the 0, which just represents the original. Because when n is 1, that's going to represent first derivative. When n is 2, that's going to represent second, third, fourth. I always say to go to at least 4. A lot of times I feel like they go to 6. But is that what you're seeing in the answer keys?
For like the homework things. Yeah.
They tend to go to 6 is what I feel like. But minimum 4 is going to, I'm going to go ahead and go up to 6. So we're going from the n being the 0, the original, up through the 6th derivative. Now, the middle column then is just me saying f to the n of x. So like f of 0 is just the original function. What's the original function? Natural log of 1 plus x. Now, so when n is 1, that's saying this is f of 1 right here, or f1 is an f prime. I'm tongue-tied here. So first derivative. So what is the derivative of natural log of something? 1 over that something. And officially we need to say times the derivative of that something. What is the derivative of 1 plus x? Just 1. So we don't actually have anything else we need to times by. Now, we can write it as 1 plus x, and that will be great when we plug in 0 for the third column. However, for the benefit of taking the rest of my derivatives, this is 1 plus x raised to the negative 1. So I like both there, because I like the 1 over 1 plus x for when I plug 0 in, but I like the negative exponent for when I do my next derivative. Does that make sense? So I'm going to have both in there. And I didn't really do both on the answer key. So now, okay, so I'm going to go ahead and do all my derivatives. The derivative of 1 plus x to the negative 1. Multiply by negative 1 out front, so negative 1 plus x. Subtract 1 from the power, so negative 1 minus 1 is negative 2. In other words, what's the derivative of something to the negative 1? Multiply by the power up front, subtract 1 from the power. Officially, it's times the derivative of 1 plus x, but there is no derivative other than 1. When we go to plug that in, 0 into that, I mean, if you want, you can think of it as negative of 1 over 1 plus x squared. That's more of a plug-in value looking thing. Like I can plug in 0 better to that than I can the negative exponent. Okay, what's my third derivative? Negative 2 times negative 1 is going to make it positive 2 out front times 1 plus x to the subtract 1, and it's negative third. If I put this as a fraction, it's 2 over 1 plus x to the third. And again, that'll just be easier to plug our 0 into. Next derivative, power of negative 3 multiplied out front. So negative 3 times 2 is negative 6. Times 1 plus x to the, subtract 1 from the power, negative 4. So now I have a negative 6 over 1 plus x to the 4th. We keep going the fifth derivative. Multiply negative 4 out front. Negative 4 times negative 6 is 24. 1 plus x to the, subtract 1 from the power, negative 5th. As a fraction, it's 24 over 1 plus x to the 5th. One more derivative. Multiply the negative 5 out front. Negative 5 times 24 is negative 120 over 1 plus x to the negative 6. As a fraction, negative 120 over 1 plus x to the 6th power. Okay. Okay. Officially, we need the third column here, don't we? The third column is f of n of 0. So it's the nth derivative evaluated at 0. Basically, take everything in your middle column and put it in 0, right? So in the first one, it's the natural log of 1 plus 0. So what is the natural log of 1? 0. The next one, I'm going to use my fractions. 1 over 1 plus 0. 1 over 1, so 1. Next one, it's a negative, so I know it's going to be negative, of 1 over 1 plus 0. So negative 1. Plug in 0. 2 over 1 plus 0 to the third. So that's 2 over 1 to the third, which is 2. Notice here my denominator is 1 every time, isn't it? So it's really all about the numerator. Negative 6 over 1 plus 0 to the fourth. Negative 6. 24 over 1 plus 0 to the fourth. And negative 120 over 1 plus 0 to the fourth. Or to the sixth. Okay. Do you remember how to do this? Okay. So the first one, we're going to use this column of numbers. And the first one, I'm going to say the 0 over, and then it's always 0 factorial in that first one. And then it's x to the 0, which is just nothing. So I don't usually write anything. Plus. Now we're going to do when n is 1. Well, we got 1 in the right column, plugging it in, over 1 factorial x to the first. Plus. Okay, when n is 2, we got negative 1, 2 factorial x to the second. It's all about the 2's. Now we're going to go all about the 3's. When n was 3, we got 2 over 3 factorial x to the third. When n was 4, we got negative 6, 4 factorial x to the fourth. When n was 5, 24, 5 factorial x to the fifth. And when n was 6, negative 120 over 6 factorial x to the sixth. And officially I should say dot, 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 because it keeps going. Now, I would always check into some cleanup here. This one cleans up pretty nicely, doesn't it? Okay. 0 divided by 0 factorial. It's just going to be 0, because 0 factorial, remember, is 1. 0 divided by 1 is 0. It's gone. 1 divided by 1 factorial, x to the first. X. Got it. Now, plus negative, I'm actually going to write it as minus. And this is one, because it gets messier as I go, I'm not going to leave the factorials. And part of this is I know how it cleans up, okay? But what is 2 factorial? That's 2, right? So this is minus 1/2 x squared, or x squared over 2. And 1/2 x squared would be just fine. My next one is positive. 2 divided by 3 factorial. Well, 3 factorial is 6. 2 over 6 reduces to 1 over 3. And so I'm going to say x cubed over 3, or 1/3 x cubed. My next one is negative, so I'm going to say minus 6 over 4 factorial. Well, 4 factorial should be 24. So 6 over 24 reduces to 1/4.
So could you take the last factorial and just multiply it by the numbers? Like, the last factorial was 6, so I could just say it was 5 by 4. And then this one was 24, or I just multiply by 5. The next one.
I'm not understanding what you're saying.
So the 3 factorial was 6, and so I could just look at that, and for the next one, I could just say multiply by 4.
Yes.
Okay.
Okay, yeah. So right there, since I know 4 factorial is 24, then okay, 24 times 5 is whatever 5 factorial is. Yes, you can do that. And that's a good way to do it. So 5 factorial is 120. 24 over 120, guess what? Are you seeing the pattern here? Ends up being 1/5. So this is plus x to the 5th over 5. Next one's minus. Hey, guess what? It's a 120. If you think about it, 5 factorial was 120, right? So this is 120 times 6, which is just going to be 1/6. So x is 6 over 6. Plus, I can say dot, dot, dot. Okay? So there is your Maclaurin series.
So on the test, will we have to do all the factorials? Would you want us to, like, actually simplify them?
Depends on the situation. I mean, if it's just something where you just have the factorial, there's some we've just left as factorials. On this one, I mean, 24 over 5 factorial, 120 over, those aren't pretty. But then once you catch the pattern, that's pretty. So it just kind of depends on the situation.
I'll just do it just in case.
Okay?
And then do you want the dot, dot, dot as part of the answer, or do you take it off?
I don't usually necessarily take off for it, but technically the Maclaurin series, they didn't tell me how far to go, so technically it goes there. And as I said, as long as you have 4, if you can't tell what's going on after 4, you need to go a little farther. I mean, we probably had it figured out at 4 in this case, but.
Well, okay, my thing was, I didn't know how to get the derivative, like keep going with the derivative.
Okay, so you need help
that
remembering
was-
the derivatives.
Yeah, that was my biggest problem, because I know how to do everything else. Like, when we have like sine or cosine, things are so easy. But I saw the ln and I was like, I don't. I was like, I can't go that
You freaked
far.
out over the derivative.
Yeah. I
Okay.
did.
That's what my
Okay.
was.
Did I explain the derivatives well enough then?
Yeah.
Okay. And that's why I kept playing both, because I really like the negative exponents to take the derivatives, but then when I go to plug in my 0, I need to see it in fraction form. So, okay. Next. I'm trying to remember, there was some I was looking at earlier.
Number 8. I'm not good at the maximum stuff.
Are you on still
Oh, on
review page 14?
Yeah.
Okay. I guess the number 8 is not a maximum stuff, so. I'm going to go to another page. This is review sheet 14, number 8. A ball is thrown vertically upwards off of a 200-foot tall building. Its height above the ground at time t seconds is given by the function h of t. So let me write h of t down because I can guarantee I'm going to need it. So h of t is 200 plus 8t minus 16t squared. Determine the time when the ball will reach its maximum height. So there's a couple of different ways we can think about this. If you just hear the word maximum, what should go through your mind? We're going to find a maximum.
Second derivative? Or is it just first derivative?
First derivative.
Okay.
Yep. Maximum, we just want to look at first derivative and look at critical points. Okay. Now, the other thing here is a height. This gives the height of the ball. And we want to know the maximum. So when do we have a maximum height? And if you're throwing a ball up, that's when the velocity of the ball is temporarily 0, right? And I realize here I'm talking more to my non-physics people last year, which is, you guys are the ones that need a little more help with this. But the velocity, in order to find like the height, that's when the velocity is briefly 0 before it starts falling back down. And velocity is the first derivative of height or position. Sounding familiar? Okay. So h prime of t is also going to be velocity. So derivative of 200 is gone. Derivative of 8t is 8 minus the derivative of 16t squared is 32t. So in order to find the maximum, we want to know when the velocity, also the first derivative, equals 0. And so we're going to set 8 minus 32t equal to 0. Subtract my 8 over. Divide by negative 32. And 8 divided by 32 is going to be 1/4. And this again was when velocity equals 0. And in this case, we just came up with one critical point. And based on the fact, if you go back and look at your height formula, it was a negative t squared. What's a negative t squared? Or a negative x squared, that's an upside down parabola, yes? So on an upside down parabola, the only critical point is a maximum at top. And so right there in the question, determine the time when the ball. So do I need to know the actual height? No, just the time when the ball hits that height is at 1/4 second. If you can measure such a thing as 1/4 second. No, it's not bad at all. And that's where half of you haven't had physics, and that makes a difference. Okay, moving along.
I have one, but I just asked for one, so I don't
Just go ahead.
If no one else is asking for it, go for it.
Well,
Or if no one else is asking for anything.
number 12 on 13. That one's another maximized one. This is probably the one that I'm more worried about.
Read my mind.
But this is a more difficult maximized one. This is not the physics maximized. This is more the maximized one that all of you are more likely to struggle with, as opposed to the physics one where half of you are a little better off than the other half. So, okay, I'm going to keep it on the same screen. This will be our max screen. This is from page number 13, or review 13. This is number 12. Then is on a maximize goal here to figure it all out.
Yeah.
This is totally different on this one, really. I mean, other than how are we going to find a max? We're going to find the first derivative, set it equal to 0 to find our critical points. The difference here is they didn't give you an equation. We have to figure that equation out. That's the harder part here. You want to enclose a rectangular plot of land that borders a straight river. because all rivers are straight, and that makes perfect sense. Okay, so that's my river there, the side that's extended. You have 75 feet of fencing. And no fence is needed along the river. So the cows get to drink from the river, right? Or horses or whatever livestock we're talking about here. What dimensions would maximize the area? So if we're trying to maximize the area, we need an area formula, right? What do you know about an area? Length times width. And what they generally tend to do is they tend to make the two that are the same x, the other one's y. So, excuse me. If we say area is length times width, area of this rectangle is really, instead of length times width, I'm going to say x times y. However, when I do this derivative and I try and find a critical point and maximize, I need one variable. I can't have x and y. So this is where, what other information did they provide? 75 feet of fencing. That is a perimeter. And it's a perimeter of what, though? Is it a perimeter of all four sides? It's just a perimeter of the three sides that need a fence. So that perimeter is x plus y, if you will. I don't know why I just wrote that as x plus x. I really should have said 2x plus y is 75. So right there, there's my connector. That is my equation that connects x and y. Now, you could technically replace either or, but which variable is easier to solve for here? It's easier to solve for y, which is going to put us in terms of x, which is our area where we're more comfortable. So if we solve for y, subtract the 2x over, and I'm going to have 75 minus 2x, or if you prefer, negative 2x plus 75. Now, what do we know? This is our y, yes? Where can I put it? Into the area equation. So now area is going to be x times 75 minus 2x. Don't try and find a derivative until you distribute. So my area equation is 75x minus 2x squared. Because we're trying to maximize, take the derivative, find that, set it equal to 0 to find that critical point. So a prime, derivative of 75x is 75, minus derivative of 2x squared is 4x. In order to find a critical point, we set our derivative equal to 0. If 75 minus 4x equals 0, let's see, negative 4x equals negative 75. X is 75 fourths, which appears to be what I left it on the paper as. Okay, pause. What are we being asked to find here? Because that makes a difference of what we do next. The dimensions. Okay, so the dimensions, this is x. Well, if you go back and look at the picture, guess what? X is one of my dimensions, isn't it? So that's one of my dimensions. What's my other dimension? Y. How do I find y? Plug x into that equation right there, yes? So 75 minus 2 times 75 fourths 75 minus 75 halves. If I get a common denominator, that is 150 over 2 minus 75 over 2, which is 75 over 2. Looking back at my drawing, x and y were my dimensions, yes? So what are the dimensions that would maximize the area? 75 fourths by 75 halves. But technically they are feet. Okay. If it asked you to actually find the max area, one option is to multiply those two numbers I just got. Or we could have taken our x value and put it back into one of those equations right there. One of our area before we took the derivative equations. Sounds like films class is noisy next door.
Sounds like Ireland.
Or is it still films this semester?
Yeah, it is.
Is it? Okay. I didn't know if that was whole year or semester. Films is a semester course, but
Yeah.
They flip with speech.
okay.
If any of us ever like get hired on a ranch, we gotta like build this.
What?
We're gonna be basically
And we just desperately
If it's at the end of the world, and they're like.
So back to the whole teacher discussion. If Shiley's trying to figure out a new game plan, if he decides he doesn't want to go into teaching,
I know you want to.
he's got some ranching and building fence information here.
I know who I'm gonna call in a few years.
I have 75 feet.
Okay. We have a little over 5 minutes. Depending on what you pick, we can do something else. And Ethan can pick, or there's 3 others in here that can pick. So if you have something that looks like a good one, I don't care. If you just look at it and it's freaking you out, let's do it.
Either 8 or 10 on 13.
8 looks rough.
8, I think, is rougher than 10.
Yeah.
Yeah.
Because 10 isn't that rough.
I think 10, once you look at the answer key, it'll be a little less rough. Again, always stop in and ask me, though, if I think 8 would be, you said on 13, yes? Make sure I'm looking at the correct number 8. So, y equals e to the, is that 5x squared minus 2? Tangent 3x squared plus 1. That was a big old rough equation, if you ask me. They want us to find y prime. Makes it look so easy, right? There's y, find y prime. A couple of things you've got to pinpoint out here. It's e to something times the tangent of something, yes? Or realizing the e and the tangent are being multiplied. There's derivative rules for e, there's the derivative rules for tangent, so this is a product rule. Derivative of the first, keep the second. Plus, because it's product rule, and then flip-flop, right? Okay, let's do it. Derivative of e to some power. Oh, wait, let me see. Is this the order I did it on here? I'm guessing, yeah. Derivative of e to some power is e to that power times, and this is where we have to think chain rule, derivative of that power. What's the derivative of 5x squared minus 2? And that's a 10x. So it's a derivative of e to some power times the derivative of that power. And then we just keep the tangent of 3x squared plus 1 as is. Plus, so this is why it's product rule, right? Now, I'm going to keep the e. So we're going to keep e to the 5x squared minus 2 times the derivative of tangent of something. We need to go back and memorize before Monday. What's the derivative of tangent of something? Secant squared of the same something. Okay, and then of course it's times the derivative of something. So times the derivative of 3x squared plus 1, which is 6x. Okay, realize you have two pieces here, and you can kind of clean them up a little bit. Although, now that I look at it, there's not a whole lot of cleaning, is there? Well, and I probably didn't. No, I did factor a little out there, didn't I? So there's a couple different ways we could leave this. One option. Possibly. I don't like the 10x. I guess I don't like the 10x in the middle. So I feel like I would do the 10x out front, e to the 5x squared minus 2 times tangent of 3x squared plus 1. Same thing over here. I don't like that 6x at the end. So I'd probably do 6x times the e of 5x squared minus 2 times my secant squared of 3x squared plus 1. That is an acceptable answer. Now, what I did on the answer key is I factored out a GCF. What do 10 and 6 have in common? A 2. They both terms have an x, so right here, 10 and, whoops. Okay, 10 and 6 have a 2. Both terms have an x, and both terms have an e to the 5x squared minus 2. Past that, you got a tangent and a secant, right? So now in parentheses, actually I think I might even use brackets here. Okay, go back. 10 divided by 2 is going to leave me with 5. X's cancel, e's cancel, and I also have a tangent of 3x squared plus 1. Plus, okay, go back and divide your GCF out. 6 divided by 2 is 3. X cancel, e cancels, and we're left with secant squared of 3x squared plus 1. So, I mean, really, in their own way, any of those 3 rows work. Okay? Test on Monday. 14 questions, parallel with the 14 questions that are on the review. Abby, hopefully you have realized that if you look at the actual review worksheet itself, a bunch of them are X'd out. Okay? Just worry about the ones that are still there. Before school, homeroom. Come see me if you have questions. I'll be here.
Not you though, Abby.
With the exception of Abby. Abby, come see me when you get back with questions, okay?